Good morning, class, and welcome to lesson 8.2.1, graphing reciprocal trig functions. The objective today is to be able to graph y equaling the cosecant of x. This stands for the cosecant. We'll write that out and talk about it a little bit later. And y equaling the secant of x, and y equaling the cotangent of x. Now, before we get into graphing those, let's talk about and recall some information with the sine of x and cosine of x functions. We want to talk about what they look like, as well as the domain and range and x-intercepts. If you recall, the sine function starts kind of at the origin, and then it goes to a max, comes back to the x-axis at pi. Then it goes to a minimum of -1 and then comes back to the x-axis at 2 pi. So if those are our x-intercepts for the sine function, and either using the unit circle or thinking about where the max would be between 0 and pi, we know that at pi over 2, the sine function is 1. At 3 pi over 2, the sine function is a -1. So we have one period or cycle of our sine function. And if we went into our negative angles, at a negative pi over 2, the sine function is a -1, and at negative pi, it's back to 0. So there's our sine function. The domain for y equaling the sine of x the domain is all real numbers. The range, y has to be less than or equal to 1, greater than or equal to a -1. And for our cosine function, recall the cosine function starts at a maximum of 1 when x is 0. And at pi, it's at a -1. And at 2 pi, it comes back to 1. The cosine of pi over 2 is 0. And the cosine of 3 pi over 2 is 0. So here's one cycle of our cosine graph, or again, one period of the cosine graph. If we went into our negative x values, the cosine of a negative pi over 2 is 0. The cosine of a negative pi is a -1. So that's what our cosine graph looks like. Now for y equaling the cosine of x, our domain is all reals. And the range, y is less than or equal to 1, greater than or equal to -1. X-intercepts for both of these functions. The x-intercepts for the cosine looks like they occur at pi over 2, and then at 3 pi over 2, and if we kept going at 5 pi over 2. So another way to write that would be pi over 2 plus pi times n. For our sine function, our x-intercepts All right, 0, pi, 2 pi, so on and so forth. Another way to write that would be we have pi times n. Just a quick review of cosine and sine. And what about the tangent function? You might want to just go to your calculator, type in tangent, kind of see what the graph looks like. Remember, tangent is also sine of x over the cosine of x. So if you look at your cosine graph on the previous page, it has x-intercepts at pi over 2 plus pi n. Well, that's where the cosine is 0. And anything divided by 0 is undefined. So at pi over 2, the tangent function really has what's called a vertical asymptote. And at all of these multiples, so at pi over 2, at 3 pi over 2, 5 pi over 2, so on and so forth. Or going the other direction, negative pi over 2. And our tangent of 0 would be the sine of 0 divided by the cosine of 0, which gives you 0 over 1, or just 0. And we could do that with pi over 4 and a few others. But your tangent graph is going to look something similar to this. And it's just a repetitive pattern. So there's tangent, the domain for the tangent graph is all reals except, so x cannot be that pi over 2 plus pi n. The range is going to be all reals because the graph keeps going up. And our x-intercepts well, it looks like it's crossing at 0, pi. Oh, those are the x-intercepts for the sine function. So it's going to be pi n. So really what we have here is your x-intercepts for tangent are your x-intercepts also x-intercepts for sine and our domain restriction, where it's undefined, happens to also be the x-intercepts for the cosine. Now that we've reviewed those things, we're going to take those graphs and help us to determine cosecant, secant, and cotangent. So far in this course, you have worked with 3 trig functions, sine, cosine, and tangent. There are 3 more, cosecant, secant, and cotangent. They're useful for changing division to multiplication in complex expressions, and in calculus to convert one trigonometric expression into another form that is easier to work with. The three other trigonometric functions are defined as the reciprocals of the three you already know. In this lesson, you'll extend your understanding of the graphing reciprocal functions to graphing the reciprocal trigonometric functions. Now, we didn't spend much time, if any, of graphing reciprocal functions this year, but we're going to still try to talk a little bit about that so that we can use those skills to graph the reciprocal trig functions. So what we have is cosecant. The function called the cosecant is the same as 1 over the sine. Our secant function is the same as 1 over cosine, and our cotangent function is the same as 1 over the tangent. So let's take a look at these graphs one at a time. What I'd like you to do is take a couple minutes and, well, first of all, pause this and take a couple minutes to complete the table for sine. Okay, if you took your unit circle and used that to help complete the table, or you did it from memory, or maybe you didn't pause it and just looked at this, that's fine. But here is what we have for the sine function. Now, we're going to take and do the reciprocal of each of those outputs. That's what this is saying, 1 over the sine of x. So we're going to take 1 over 0. Oh, wait a second. What is 1 divided by 0? Anything divided by 0 is undefined. I'm just going to write undefined. That's going to be short for undefined. Now, at a negative 3 pi over 4, my sine function is a negative square root 2 over 2. The inverse, or excuse me, the reciprocal of that, 1 over a negative square root 2 divided by 2 is equal to, take the numerator, multiply by the reciprocal of the denominator. And so now we have a negative 2 over the square root of 2, but we need to rationalize our denominator. So I'm going to multiply by the square root of a giant 1, square root 2 over 2. And that's going to give me a negative 2 root 2 over the square root of 4, which is 2. Let's simplify that. 2's cancel, and we have a negative square root 2. Well, 1 over a negative 1, well, that's just equal to a negative 1. Oh, another negative square root 2 over 2. So I could go through these steps again. Take 1 over negative square root 2 over 2, and we're going to get a negative root 2. 1 over 0. Again, that's undefined. And here's a positive square root 2 over 2. 1 divided by square root 2 over 2. Well, I'm going to go through the exact same steps here, but I will end up with a positive square root 2. Oh, 1 over 1 is positive 1. Another square root 2 over 2. So that's going to be 1 over the square root 2 over 2. We'll simplify it to the square root of 2. 1 over 0. Again, undefined. 1 over a negative square root 2 over 2. So we're dealing with this right here. Again, that's going to give me the same thing that I've had in the past, a negative square root 2. 1 over a negative 1 is a negative 1. You just got to keep thinking to yourself, we're taking 1 over all of these output for all of the sine output values. So we're just taking 1 over each of these. Come on. So now 1 over a negative square root 2 over 2 is a negative square root 2. And 1 over 0 is undefined. So let's try to graph this. If I want to graph 1 over the sine function, I have vertical asymptotes at pi, negative pi. There's a vertical asymptote because it's undefined. At 0, at pi, and at 2 pi. Now I also know that at the pi over 2's, my output is either 1 or a negative 1. So at a negative pi over 2, I'm at a negative 1. At pi over 2, I'm at 1. At 3 pi over 2, I'm at a negative 1. What about our pi over 4's? Take your calculator and take the square root of 2, and you're going to get 1.414. So this is going to be a negative, let me change color. This is going to be a negative 1.41. So that's at negative 3 pi over 4, negative 1.41 is somewhere right around here. Maybe a little bit further down. I'm at negative pi over 4 for x. My output is a negative 1.41. That's going to be right there. Now, if I was to connect these, here's what's happening. I'm actually creating this type of graph. Kind of looks like an upside down parabola. And we'll talk about why in a few more minutes. Let's finish graphing the inverse sine. Now if I take and look at positive square root of 2, that's going to be a positive 1.41. So when x is pi over 4, I have a positive 1.41. And at 3 pi over 4, I have another positive output of 1.41. And that creates something that looks kind of like a parabola opening up. Now they're not parabolas, they just look like them. We're going to call them hills and buckets. And at 5 pi over 4, I'm back to a negative 1.41. And at 7 pi over 4, again, another negative 1.41. So now I've got another upside down bucket. The question for us to understand is, why does this occur? Why do we get these hills or upside down buckets and buckets? Well, that has to do with the sine function. If we go back now and graph the sine function starting at the origin, we know the sine function has a hump from 0 to pi. Well, an inverse of that, it means we're taking 1 over every output value. So if my output happens to be 2, excuse me, if my output happens to be 1/2 at a certain spot, so say right there, output is 1/2. Well, 1 over 1/2 1 over 1/2 gives us an output of 2. So my output should be 2. And if my output right down here happens to be 1/4, then 1 over 1/4 is going to give me an output of 4. So at this point, I should have an output of, I guess it would be pretty close to 4. If I kept extending this graph, that's where the buckets or upside down buckets come from. Anytime the sine function has a hump, here's a hump for the sine function, you're going to create a bucket for the 1 over the sine function. Now, if the sine function itself has a bucket, you will create, let's fill that in with green. You'll create an upside down bucket when you do 1 over the sine. But we also know from the definitions on the previous page that 1 over the sine of x is the same as the cosecant of x. So in blue, we have really graphed y equaling the cosecant of x. Here's another bucket for the sine function. That's going to create an upside down bucket for the cosecant graph. Now let's answer a few more questions dealing with the cosecant graph. The domain. Our domain happens to be all reals except x cannot be where there are vertical asymptotes, and that's pi times n. Pi times n. The range, y is going to be less than or equal to 1. It's everything that's going below a -1. And think about the buckets that open up. That's where y, that's supposed to be y less than a -1, and y is going to be greater than or equal to 1. Intercepts. Where does this cross the x-axis? It doesn't. So there is none. And asymptotes, well, the asymptotes comes from the restrictions on the domain. My asymptotes are at x equaling pi n. Now, going to the next slide and try this with the cosine graph. Again, what you can do is pause this and fill in from your unit circle the cosine of each of these angles. Then come back and press play. Okay, so we have now put in the values for the cosine of each of these angles. We're going to do this one a little bit differently. We're going to start by graphing the cosine. So in black, I'm actually going to graph our cosine function. And I really don't even need the table for that because we have a pretty good idea what that looks like. We did that earlier in the video. I'm going to plot my critical points, maxes, mins, x-intercepts, and going into the negative values. So we're going to carefully graph our cosine function. And now we're going to graph the 1 over the cosine, which is the same as the secant of x. To do that, we need to start by identifying the asymptotes. The asymptotes for the secant, and we'll do the secant in yellow. The asymptotes are going to occur wherever the cosine is equal to 0. So there's where it's undefined. Here's another x-intercept, or where the cosine is equal to 0. So remember, 1 over 0 is undefined. And our last asymptote is going to be at 3 pi over 2. The idea of hills and buckets that we used with the sine function and cosecant function will also apply to the cosine and secant. So wherever there was this hump in the cosine, we are going to create a bucket for the sine, for the secant. Here's a bucket for the cosine that's going to create an upside down bucket for the secant. And another partial bucket, or partial hump, that's going to create a partial bucket. And lastly, we've got a partial bucket here for the cosine. That's going to create an upside down partial bucket for the secant. Now that we've identified what the graph of the secant looks like, let's actually find the table. So these are always going to be 1 over whatever the cosine is. Let's write this out. 1 over a negative 1. It's going to be a negative 1. Here we are again, back with this idea of 1 over a negative square root 2 divided by 2. Well, we've already done that work. It comes out to be a negative square root 2. This is going to be a positive square root 2. If I take 1 over a positive square root 2 over 2, I'm going to get the square root of 2. 1 over 1 is 1. 1 over the square root of 2 divided by 2 simplifies to square root 2. 1 over a negative square root 2 over 2 gives me a negative square root 2. 1 over a negative 1 is a negative 1. 1 over a negative square root 2 over 2 is again a negative square root 2. And lastly, we're going to get a positive square root 2 and 1. Now if we go and plot all of these points, starting over here, I have a negative pi, output's a negative 1. That's right there. Negative 3 pi over 4, negative 1.41. So negative 1.41 is right in there. So we're still creating this half of an upside down bucket. And you can go through and verify all these other ones if you would like. But you're going to create a bucket for the secant function wherever the cosine has a hump. And you're going to create an upside down bucket for the secant function wherever the cosine has a bucket. Now we need to answer a few more questions for the secant graph. What is the domain? Well, the domain happens to be all reals, except where we have those vertical asymptotes, which is at pi over 2 plus every pi unit, so plus pi n. Now, what is the range? The range is kind of unique because it goes from 1 up, that's this stuff right in here, 1 up, and a negative 1 down. So y is going to be less than or equal to a negative 1, and y is going to be greater than or equal to 1. The intercepts, well, there isn't any, because these buckets are opening down, going away from the x-axis, or opening up, going away from the x-axis. So there is none, or however you want to write that. In the asymptotes, well, that comes from your domain. X cannot equal, I had to change that in the domain, x cannot equal pi over 2 plus pi n. And so my asymptotes are at pi over 2 plus pi n. Let's make a graph for the tangent and the reciprocal 1 over the tangent. Before we do that, recall that the tangent of x is equal to the sine of x over the cosine of x. So taking the tangent of a negative pi would be the same as taking the sine of a negative pi over the cosine of a negative pi. And the sine of a negative pi is 0, so 0 divided by anything is 0. And this might help to actually write it out a little bit more. Tangent of a negative 3 pi over 4. Well, that would be the same as taking the sine of negative 3 pi over 4 divided by the cosine of 3 pi over 4. They're the same value. Take a look on your unit circle, so you're going to get 1. And if I take the tangent of a negative pi over 2, well, that's really saying, I'm going to write this one out, the sine of a negative pi over 2 divided by the cosine of pi over 2. Well, this is a negative 1 divided by 0, which is going to be undefined. So this is undefined. If you do a the tangent of a negative pi over 4, you're going to get a negative 1. The tangent of 0 is 0. The tangent of pi over 4 is 1. The tangent of pi over 2 is undefined. The tangent of 3 pi over 4 is a negative 1. Tangent of pi, 0. The tangent of 5 pi over 4 is 1. Tangent of 3 pi over 2, that's going to be undefined. The tangent of 7 pi over 4 is a negative 1. Tangent of 2 pi is 0. Now we'll take and graph this one first. And I'm going to start by graphing the asymptotes. Asymptotes, and this is something that we did at the very beginning, are at negative pi over 2, pi over 2, 3 pi over 2, and plotting the point negative pi, 0, negative 3 pi over 4 1. I get this for my graph. Plotting these next series of points, a negative pi over 4, negative 1, 0, 0, pi over 4, 1. Here's what this looks like. It's that little S curve. And the next series of points, right through here, 3 pi over 4, negative 1, pi 0, 5 pi over 4, 1, another S curve, and plotting the last two, 7 pi over 4, negative 1, 2 pi 0. There's our tangent graph. Now for the cotangent, if the tangent is sine over cosine, and I'm going to go with 1 over the tangent of x, that's the same as the cotangent of x, then I have to take 1 over the tangent, which means I'm going to take 1 over the sine of x divided by the cosine of x, and that is equal to cosine of x over the sine of x. So if you want to make a cotangent graph, you're actually going to be graphing the cosine of x divided by the sine of x. That's equal to the cotangent of x. So if you go to your unit circle, and take a look at the cosine over the sine at a negative pi. And what you're going to find out is that is actually 1 over 0, which is undefined. And if you go to a negative 3 pi over 4 and take a look at the cosine over the sine, you're going to get 1. And if you go to a negative pi over 2 and take a look at the cosine over the sine, you're going to get 0 over a negative 1, which is just equal to 0. Now let's keep doing a few more of these. If you take a look at the cotangent or the cosine over the sine at a negative pi over 4, you're going to get a negative 1. If you look at the cosine over the sine at 0, excuse me, you're going to get 1 over 0, which again is undefined. Now let's just stop there and graph what these 4 or 5 points. So at a negative pi, I have a vertical asymptote. At 0, I have a vertical asymptote. And in between, negative pi over 2, I have an x-intercept of 0. At negative 3 pi over 4, I'm at a positive 1. And at negative pi over 4, I'm at a negative 1. And if I connect these, I have another S-curve, just going in a little bit different direction, different x-intercepts, different asymptotes. Now let's repeat that. Let's see if I can highlight this. Let's take all of this that we just did and then shift it over for our next cycle. So all of these outputs, they will also be the outputs over here. So if I take a look at the cosine of pi over 4 over the sine of pi over 4, well, that's the square root of 2 over 2 divided by the square root of 2 over 2, which is 1. This is going to be the cosine of pi over 2, which is 0, over the sine of pi over 2, which is 1. That gives me 0. This is the cosine of 3 pi over 4 over the sine of 3 pi over 4. That's going to be a negative 1. And the cosine at the cosine of pi over the sine of pi, that's going to be undefined. Let's plot these points here. Now I've already got the first vertical asymptote at pi over 4, 1, at pi over 2, 0, and at 3 pi over 4, negative 1. And then another vertical asymptote at pi. If I connect it, there's our tangent graph. And I'm not going to finish filling out the table. I am going to copy this graph over. I have to have another vertical asymptote at 2 pi. And my graph has to pass through this point, and this point. There is the graph for the tangent. Let's answer a couple more questions. I got a typo down here. We're going to be y equaling the cotangent x. In our domain, well, our domain is all reals except for where there are asymptotes. So x should use blue here. X cannot equal 0, pi, 2 pi. That's called pi times n. My range, well, it keeps going up and down continuously, so that's going to be all reals. And my intercepts, well, it's crossing at pi over 2, 3 pi over 2. So my intercepts are pi over 2 plus every pi unit, so pi n. And the asymptotes, well, that's going to, again, come from your domain. If we write it as an equation, that's x equaling pi over n. Now, I want you to be very careful of your asymptotes in your domain. This is a domain restriction. We're really saying that the domain is all reals except pi n. Except, same as not equals. Versus when you talk about your asymptotes, you're talking about the equation of a line. So that's why one of them says equal and the other one says not equal to. Hopefully some of this is making a little bit of sense so that you can try this challenge problem. What I'd like you to do is graph, and you can use your notes from the couple previous slides, graph the secant of x plus 2. I'll give you a hint. This is just a transformation up 2. So pause this, see if you can graph it. If you need to use the table, that's great, and then come back and check your work. Okay, welcome back. I built the table for the secant. I'm just using the table from the previous slide. And then I added 2 to each one. So remember, the square root of 2 is the same as 1.41. So this was a negative 1.41, and then I added 2 to it, and I got 0.59. 1.41 plus 2 is 3.41. Then you can plot those points. I didn't. I just used our buckets in upside down buckets from the secant graph, and I just moved everything up 2, just a transformation vertically of 2. The vertical asymptotes did not change. You can see in blues where your graph of the secant of x plus 2 should look like. Hopefully you enjoyed this lesson. Wishing you all the best as you move through Chapter 8 and enjoy the weather this week.